Welcome to the Chemistry, Biology, and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry, Unit 2 for October 2021. This is the Part 2 video. I'll put the link to the Part 1 video below the description box. Let us begin with the first question of Section B. Section B, question 19, it says, this question is about enthalpy changes. An experiment was carried out to determine the enthalpy change of combustion for ethanol. This is the equation they've given us here, and they say 1.1 gram of ethanol was burned in a spirit burner. The heat energy from this combustion raised the temperature of 100 grams of water from 21.6 to 63.9 degrees Celsius. They have given us the molar mass of ethanol, which is 46 grams per mole. So they say calculate the number of moles of ethanol in 1.19 grams. So I know this is the mass and that is the molar mass of ethanol, so we can just substitute. In this formula, number of moles is mass over molar mass, which is 1.19 divided by 46. And you get 2.587 times 10 power negative 2 mole. So here you get 1 mark. The next part says calculate the heat energy required to raise the temperature of 100 grams of water from that to that. If we want to find this, we need to find the delta T, so which is going to be the temperature change from 21.6 to 63.9. So it will be 63.9 minus 21.6, and we get 42.3 degrees Celsius. So when we substitute this into the equation, Q, which is the heat energy, is going to equal to mass times the specific capacity times delta T. They have given us the specific capacity here, so I will substitute for 0.18 in the place of C, and the mass is 100. The temperature change is 42.3, and when I substitute and calculate, I got 17681.4 joules. So I converted this to kilojoules, so it's going to be 17.6814 kilojoules. You could write this in specific significant figures based on here they've been using 3 significant figures. So I could say 17.7 kilojoules of energy. So let's continue. So here they say use your answer to A1 and A2 to calculate a value for the enthalpy change of combustion of ethanol, and they want you to give your answer to an appropriate number of significant figures and include a sign and unit. So we know this is an exothermic reaction because the temperature increased. So it means the delta H is going to be negative Q over N. And if we substitute the Q we have got previously, it is negative 17.6814 divided by the number of moles we calculated in A. And that gives us this, when I try to write it in specific significant figures, I got negative 683 kilojoules per mole. That is just 3 significant figures. I used 3 significant figures because the rest of the values were given in 3 significant figures. If I'm to take you back, we can see this is 46.0, that is 1.19, 21.6, 63.9. You can see most of these, like this one, and that one were given in 3 significant figures as well as that. So I will use my final answer to be in significant figures that are 3 as well. So the next question says, the value of the enthalpy change of combustion from this experiment was very inaccurate. When they say it was very inaccurate, it means the calculated value and the data booklet value do not match. So they want you to give 2 reasons why this value was so inaccurate apart from heat loss. Since this was combustion, there is an expectation of incomplete combustion, and there is an expectation that some of the fuel escaped. So I said there could have been incomplete combustion of the alcohol. This is due to insufficient oxygen supply. And then the next part, I said some ethanol could have evaporated. This is due to when they are opening the spirit burner and then closing it in order for them to light it, some of the fuel could have evaporated. So moving on here, they say, main bond enthalpies can be used to calculate a value for the enthalpy change of combustion of a compound. They want you to give the meaning of the term main bond enthalpy. So since they use mean bond enthalpies, these are averaged bond enthalpies. So I said the energy required to break 1 mole of a specific bond in the gaseous state, that is mean bond enthalpy, and it is an average or averaged over a number of different molecules. So that is what they call the mean bond enthalpy. So down here, they've given us some information. They say calculate a value for the enthalpy change of combustion of methanol using the information in the table and the equation shown. This is the equation they have shown. I try to expand out or to display the bonds here so that we can see. In methanol, we have 1, 2, 3 carbon-hydrogen bonds. We have 1 carbon-oxygen bond, and we have 1 oxygen-hydrogen. In here, this is 3/2 oxygen, so we have the number is 3/2 into 1. And here we can see these are 2 carbon-oxygen double bonds. And here we can see these are 4 hydrogen-oxygen bonds. So to use the information from the table to calculate the bond enthalpies were given. So I said to find the delta H, it should be the summation of the bonds broken minus the summation of the bonds formed. So here I began by calculating the bonds broken. So I said it's going to be 3. We have 3 carbon hydrogen, so 3 times 4, 1, 3, plus 1 times 358, plus 1 times 464, plus 3/2 times this one here, 498, and that gave me a total of this. Those are these bonds here. And then on the other side, the bonds that are formed, we have 2 carbon-oxygen double bonds, which is that 2 times 805, and then we have 4 oxygen-hydrogen, so it should be 4 times 464, and I got this one here. So I have the 2 sums. To find the delta H, it should be the summation of the bonds that are broken, which is this one here, minus the sum of the bonds that are formed. And when I substituted it here, I got negative 658 kilojoules per mole as the enthalpy change using the main bond enthalpies. So moving on. Here they say enthalpy change of combustion can be used to calculate the enthalpy change of formation of a compound. So here we have the information in the table. They want us to use this data here and the Hess cycle here to be able to calculate the enthalpy change in question. So they said complete the Hess cycle and use it to calculate the standard enthalpy change of formation of ethanol. So here we are given the elements and we can see they are used to form ethanol. So this is enthalpy of formation of ethanol. However, when ethanol is burnt, we produce carbon dioxide and water. Since they've given us the enthalpy of combustion, it means we are going to use a combustion process here. To burn ethanol, you produce carbon dioxide and water. However, we have to balance the carbons. Here you see there are 2 carbons. The hydrogens are 4. So since hydrogens are going to produce water, so we say 2 hydrogen, that is going to be twice water molecules. The oxygen is going to be 1 here. We can see from here is 1. So the other oxygen is going to be provided from here, which should be as well 5/2. And then that's it basically. The carbons are 2. Oxygens have to be balanced by the oxygen that is going to be supplied here. On the other side, we have 2 carbons here, so they end up here. And then we have 4 hydrogens, they end up here. And we have a half oxygen. So add up these, we form the oxygen that is going to be produced. Remember, in total, this is going to produce 4 oxygens, and that is going to produce 2. So there will be 6 oxygens in total. That means we will add 5 oxygen atoms, and since oxygen comes as a molecule, it means here we're going to add 5/2 oxygen molecule, as we can see that, which creates 5 oxygen atoms, and that will also be 5 oxygen atoms. So when we substitute all that to find that enthalpy change, it's going to be that plus that if you reverse it in the other direction. So here we have to know how many carbons are there. Enthalpy of combustion of carbon is negative 394, so 2 times that because 2 carbons are being burned. And enthalpy of combustion of hydrogen, it has to be that times 2, since 2 of them are being burned. And then the enthalpy of combustion of these, it's 1 mole, so it has to be just negative 1167 kilojoules per mole. Substituting that, so these ones here have to be in the same direction. So that plus that, and then plus that. This sign is going to be positive here, as you can see. And then the final answer was negative 193 kilojoules per mole. So this brings us to the end of question 19. Let us continue to question 20. Question 20 says, this question is about halogenoalkanes. They say the rate of hydrolysis of 1 chloropropane, 1 bromopropane, 1 iodopropane in reactions with aqueous silver nitrate solution were compared. They want you to state what would be measured in the experiment to compare the rates of hydrolysis. Now, when these hydrolysis reactions are carried out, halides are going to be produced. So there is going to be silver chloride, silver bromide, and silver iodide, and they will look at the precipitates that are formed either the color of the precipitates, and in this case, since we are measuring the rates of hydrolysis, it should be the time taken for the precipitates to be formed. So here I say the time taken for the silver halide precipitates to be formed. So how long does it take for the silver iodide to form, the silver bromide to form, and the silver chloride to form? That will be what's going to be measured. The next part says state which of these halogenoalkanes would hydrolyze the fastest, and they want you to justify your answer. In this case, it is going to be the iodopropane bond is going to be the weakest among the three, and therefore it's going to be broken easily, leading to the release of the iodide, which is going to bind to the silver, producing the silver iodide. The next question says, the equation for the hydrolysis of 1-chloropropane by aqueous hydroxide ion is shown below, which is this one here. And then they say, give the mechanism for hydrolysis, including curly arrows and relevant dipoles and lone pairs. So I displayed this part here because I wanted to show you the partially positive carbon. This is a partially positive carbon, and that is a partially negative chloride. So this is going to be a substitution reaction. So we expect the incoming nucleophile to have a lone pair of electrons that is going to be donated, or that are going to be donated to the partially positive carbon. And then this bond is going to break as chlorine atom takes away the bond electrons to form chloride ion. So in the process, that is going to attach to that carbon with a dative covalent bond, forming this, and that is how this mechanism is going to occur. Let us continue. The next part says the boiling temperature of some halogenoalkanes are shown. So we see chloropropane, that is the boiling temperature, 1 bromopropane, and 1 iodopropane. So they want us to explain the trend in boiling temperature of these halogenoalkanes by comparing the intermolecular forces involved. They say detailed explanations of forces involved are not required. So we can see iodopropane has the highest boiling temperature, and since these are halogenoalkanes, they do have permanent dipoles and they do have London forces. So here I said all the three halogenoalkanes contain London forces and permanent dipoles. Chlorine, being more electronegative than bromine and iodine, makes its permanent dipoles to be stronger, and the permanent dipoles in iodopropane to be the weakest. So that point also earns your mark. Then I said, however, iodopropane contains more electrons than 1 bromopropane and chloropropane, and this is going to lead to more London forces being formed in 1 iodopropane in comparison to the others, and there will be more energy required to overcome these interactions, meaning the London forces, and therefore 1 iodopropane has a higher boiling point in comparison to the 1 chloropropane and 1 bromopropane. So let's continue. Here they say in another experiment, 2-bromobutane is heated with ethanolic potassium hydroxide and an elimination reaction occurs. Remember, this is a halogenoalkane. We are heating with potassium hydroxide. If an elimination reaction occurs, that should be alcoholic. The condition should be alcoholic. So they say draw the skeletal formulae of the 3 possible organic products, giving their names. So this is formation of an alkene from a halogenoalkane. So for the first one, I drew this part here. Remember, they've told us 2-bromobutane, which is going to be this. If this is 1 carbon, the second, the third, and the fourth, so the bromine is here. It means elimination can occur creating a carbon-carbon double bond here, or a carbon-carbon double bond here. So when it creates a carbon-carbon double bond here, we have that only, because at the end here, we have 2 hydrogens, and therefore, we do not have any priority groups, so this cannot be a geometric isomer. However, when the carbon-carbon double bond forms here, we have priority groups. There is this carbon, and here there is hydrogen. Here there is going to be a carbon, and there is going to be another hydrogen here. So that means we can produce 2 geometric isomers, which is the E-butene and the Z-butene, as you can see displayed here. So those are the possible isomers or organic products that could be formed. And this brings us to the end of question 20. Let us continue to question 21. Question 21, this question is about group 1 metals. So they say, when potassium is placed into a beaker of cold water, potassium hydroxide and hydrogen are formed. They say, write an equation for this reaction and include state symbols. They've given us the product, so just write potassium plus water gives us potassium hydroxide and hydrogen, and then balance the equation. To balance the equation, we see that we have 1 hydrogen here, 2 hydrogens here, so those are uneven numbers. So to create a 2 here, and that makes a 2 here, which will make a 2 here. The state symbols are, this is a solid, that is a liquid, because they said cold water, so that is a liquid, and that is aqueous because hydroxide of potassium is soluble, and here we will see that is a gas. The next part says this is a redox reaction, and they want us to state which element is oxidized and which is reduced, and they want us to justify our answer by giving the initial and final oxidation numbers of any element that changes oxidation state. When we observe here, we can see that this potassium is a solid here, and it's converted into an ion, so that means potassium is being oxidized as its oxidation state is moving from 0 to +1. We also see hydrogen being oxidation state 0 from +1 oxidation state, so hydrogen is being reduced. So here I said hydrogen changes from +1 to 0 oxidation state, so it is reduced, and potassium changes from 0 to +1 oxidation state, so it is being oxidized. The next part says the reaction of potassium with water is very vigorous and a flame is seen. They want you to state the color of the flame. Because this is potassium, the flame should be lilac in color since potassium cation gives off a lilac flame. Continuing on, they say the laborer has come off a bottle known to contain M, a group 1 metal which is stored in oil. That is a reactive group 1 metal. So they say a student carried out an experiment to determine the identity of M. The procedure is as below. In step 1, they say a small piece of M was wiped with tissue paper to remove the oil. The piece of M was weighed and placed into a beaker of distilled water. In step 2, they say after the reaction had finished, the contents of the beaker and the washings were transferred to a 250 centimeters cube volumetric flask, and the solution was made up to the mark with distilled water and mixed thoroughly. So a standard solution was produced here. And in step 3, they say a pipette was used to transfer 25 centimeters cube portions of this solution to conical flasks. Each portion was then titrated with hydrochloric acid of concentration 0.4 mole per decimeters cube. So as we can see here they've given us the table of results. They say the mass of metal M is 0.37. You remember they weighed this. This is the mass dissolved in 250 centimeters cube in the volumetric flask. And they say the mean titer of the hydrochloric acid is 12.80 centimeters cube. So that is what came out of the burette. And then they say the reaction taking place is shown below as that. And the indicator used was phenolphthalein. They want you to state the color change at the end point. In this situation, phenolphthalein is going to turn from pale pink to colorless. So you get 1 mark for that and 1 mark for that. Let us continue. Here they say calculate the relative atomic mass of M and use it to identify the group 1 metal M. So I rewrote the equation here and the information I got from the question. Remember, they've told us the titer is 12.8, that is for HCl, and the concentration is 0.4 mole per decimeter cubed. Also, the volume of the MOH used was 25 centimeters cubed from the 250 solution that was made. So since I have all the information for this, I calculated the number of moles using that, which is concentration times volume. That is the concentration. This is the volume converted to decimeters cubed by dividing by 1,000. And when I multiply this, I got 5.12 times 10 power negative 3 mole. Now, when we look at the reaction equation, we can see the mole ratio is 1:1, and that means the moles of this are exactly equal to the moles of that in the 25 centimeters cubed. So that's why here I said the moles of MOH in 25 centimeters cubed is that. Those are the moles that reacted. However, the MOH was taken from 250 centimeters cubed, so I have to find the moles of MOH in 250 centimeters cubed. To do that, I multiply that by 10, and it gives me 5.12 times 10 power negative 2 moles. Now, you remember I know the mass at the beginning. I was given the mass as 0.37. So in this case, I know 1 mole of the metal hydroxide contains 1 mole of M. So the moles of metal of the M in the 250 should equal to the moles of the MOH. I don't know if you can understand that. MOH contains, if 1 mole of this contains 1 mole of that. So the moles of this should equal to the moles of that, and the moles of this should equal to the moles of that. So moles of M are equal to the moles of MOH in the 250 centimeters cubed, and therefore they will be exactly that. Now, to find the molar mass, it should be mass divided by number of moles, which is the weighed mass divided by the number of moles, and the answer comes off as 7.23 gram per mole as the molar mass. So from the estimation and looking at the periodic table, M should be lithium. Next they say, another student repeated the experiment using a different sample of metal M, but did not wipe off the oil before weighing it. They want you to state how this would change the calculated value of the relative atomic mass of M and justify your answer. If they did not, if they weighed without removing the oil, so it's going to be estimated that some of the mass that remains behind is mass of the metal, yet actually it's mass of the oil that is not going to participate in the reaction. So the estimated moles are going to be lower than the actual moles, or you would say the mass that is weighed is going to be less than the actual mass of the metal hydroxide. So here I say the weighed mass of M would be lower than the actual mass of M. Remember, it's the M that is going to be reacting, so the theta value is going to be lower due to the less moles of M. Here I also say the resultant calculated molar mass of M would be greater. So you would estimate or approximate it to be something different when actually it was not. So this brings us to the end of question 21. Let us continue to question 22. Question 22, they say this question is about ethanol and bioethanol. The main fuel used as a petrol substitute is bioethanol. They say bioethanol is ethanol that has been produced by fermentation. The starting material is usually some form of plant material rich in starch, such as wheat, maize, or potatoes. Enzymes in yeast convert this material to simple carbohydrates such as glucose, and then to ethanol and carbon dioxide, so we can see that. They continue to say the mixture is left for several days until fermentation is complete. The percentage of ethanol is never greater than 15% because higher concentrations of ethanol kill the yeast. A common blend of fuel is 95% petrol and 5% bioethanol. The engine does not need to be modified for this mixture. Then they go on to say, give one advantage and one disadvantage of using bioethanol in petroleum. So here I say the advantages, of course, is going to be sustainable, it's going to be renewable, because we can continuously plant the biological material like wheat as well as maize and be able to produce the bioethanol every time. So it's renewable, it's sustainable, and it produces fewer greenhouse gases since as these plants are growing, they use the carbon dioxide from the environment, and when we burn them as fuels, that same CO2 is returned back. So you could say they are kind of carbon neutral. Almost carbon neutral. So the disadvantage is they require a lot of land to be used. So there is a lot of land that has to be provided, and this rather be used for food production. It's going to be used for the production of these plants that are going to be used as fuels. Part B says suggest why this fermentation must be carried out in absence of air. So because air contains oxygen, and that would oxidize the ethanol to ethanoic acid, that is not what we intended to make. The next part suggests how the ethanol can be obtained from the fermentation mixture. We could use fractional distillation to be able to obtain the ethanol after filtering the mixture, because you can see ethanol could come off with some other products since they say the yield is going to be about 15%. So at the end of the reaction, we're going to have some other things or some other organic molecules that are not ethanol. So we could use fractional distillation. We know the boiling temperature or boiling point of ethanol, so we will collect the distillate at the appropriate temperature, and that will be how we can separate it. So let's continue. Here they say ethanol is hygroscopic, which means it readily absorbs water from the air. They say give a possible reason why ethanol is able to absorb water. Now, ethanol can absorb water because it can form intermolecular hydrogen bonds with water molecules, so they will interact with each other quite well. That is why it can absorb water. The next part suggests a problem arising from the hygroscopic nature of ethanol when using this fuel in a motor vehicle. Now, it means it's going to absorb the water, and the water will be contained in the biofuel, and this is going to lead to the rusting as well as corrosion of some of the parts within the engine or the motor vehicle, and that could be problematic. Another thing is water. Water is going to separate, or phase creation is going to occur, or you could call it phase separation, because water and some of the oil, because remember they use 5% bioethanol, so the other could be petroleum. So if it is going to be, there is going to be some water in there, there is going to be phase separation, and that could create problems during the combustion of the fuel. So part E says, Ethanol can also be produced by the hydration of ethene. Of course, this is ethene plus steam gives us ethanol. The enthalpy change for this is negative 45 kilojoules per mole, and this is a reversible reaction. They say typical conditions are 300 degrees Celsius, 60 atmospheres with a catalyst of phosphoric acid. So we can see this reaction is carried out at quite a high pressure, at a high temperature, yet it is exothermic in the forward direction, and they also use a catalyst. So this question is asking us to explain why these conditions are used by describing the effect of changing the temperature and pressure on the rate of reaction, equilibrium, yield, and cost. So I'm going to begin by describing it, then I'll read what I wrote. So the forward reaction is exothermic, so we expect an increase in temperature to favor the backward reaction, meaning more ethane is going to be produced and less ethanol is going to be yielded due to the higher temperature. However, a higher temperature is going to cause a rapid rate of reaction, so a high temperature of 300 is used in order to obtain ethanol at a faster rate. Even if the yield is compromised, we can still recycle the products. So it means at the end of the reaction, if there is unreacted ethane as well as water, they can be recycled so that we can obtain the ethanol, even if it's going to be less at a faster rate. And using a catalyst is going to provide an alternative pathway with lower activation energy, making more fractional molecules to have the energy equal to or greater than activation energy for this reaction to proceed. So let me continue reading what I wrote. I said, a typical temperature of 300 degrees is used to increase the rate of reaction, since more particles will have energy equal to or greater than activation energy. However, the forward reaction is exothermic and thus produces more yield of ethanol, so 300 degrees Celsius is used as a compromise between yield and rate. So in this case, I want to try to clarify on this part here. Let me use a different color. When I say the forward reaction is exothermic, increasing the temperature to this will lead to lower yield, because the forward reaction is exo. However, this is used as basically they compromise. There is a compromise between yield and rate. Yes, we know the yield is going to be lower, but the rate is going to be higher, and the unreacted reactants can be recycled in order to obtain the products in a shorter period of time. So lastly here I said, since they are gaseous species, increasing pressure leads the equilibrium to shift to the right side, producing a high yield of ethanol. So the key thing is talking about temperature, talking about pressure, and talking about the use of a catalyst, as I'm going to see here. I went on to say this is because a higher pressure increases the rate of reaction and more successful collisions can occur, so a pressure of 60 atmospheres is ideal. And then I said using a high pressure would be very expensive, so that is a by the way. And then lastly I said a catalyst provides an alternative pathway with lower activation energy, and this allows for more successful collisions to occur at lower temperature. Here they say the rate of this reaction is increased by using a catalyst of phosphoric acid. They said label the axis on the Maxwell-Boltzmann's distribution curve and use it to explain how a catalyst increases the rate of reaction. So I began by labeling the same graph. Remember, this is the same temperature curve. So this is the EA for the uncatalyzed reaction. You can see I labeled it EA uncatalyzed. So if there is no catalyst, it means the fraction of molecules with energy equal to or greater than activation energy is going to be that, which means there is less or fewer fractions. However, when we introduce a catalyst, the activation energy for that pathway is going to be lower. So it means the total number of molecules are going to be those filling up this whole area. It means there is a more fraction of molecules with energy equal to or greater than activation energy, and that means there are more successful collisions that can occur, and there is going to be a higher yield of product. So here I said, without a catalyst, fewer particles have energy equal to or greater than activation energy, so the number of successful collisions are less. Now with a catalyst, the number of particles with energy equal to or greater than activation energy are many, so there are more successful collisions and the rate of reaction is going to increase. Let us continue. So here they say, catalysts such as phosphoric acid are bound to our support material that contains lots of pores. So we can see the support material, those are the pores, and the catalysts are going to be maybe coated in those areas or around that support material. They say suggest the advantage of using support material containing lots of pores. This is to increase the surface area. So I say there is a larger surface area, so the rate of reaction is going to be faster. Creating a larger surface area means the reactants are going to have more points of contact in order for maybe adsorption, reaction, as well as desorption to occur. That is how some heterogeneous catalysts work. So the substances are going to adsorb onto the surface of the catalyst, and the reaction is going to be faster. So if you have a large surface area, it means there is a wider area for these reactants to adsorb, and therefore reaction can proceed faster. So the next part says, under these conditions, only about 5% of ethene is converted into ethanol as it passes over the catalyst. Suggests how the overall yield of this process can be improved to make it economically viable. So here we could maybe remove, because this is a reversible reaction, we could try to remove the product in order to drive yield to the product side. I'm going to show you that. Back to the reaction, give me a minute. So if we remove some of this, the equilibrium is going to be driven to the product side, and that means we can have more product, or the yield can be increased if we do that. Or we could recycle the unreacted reactants in order for them to go through the same reaction the next batch in order to increase the amount of product that can be produced. So here I said, by removal of ethanol when it is formed. When you remove ethanol after it is formed, equilibrium is going to be more inclined to the product side. Also, we could do that by recycling the unreacted reactants to allow them time to form products. So this brings us to the end of question 22, as well as the end to this video. Thank you for being with us. Please do not forget to subscribe to our channel. See you in the next video. Bye-bye.